Okay, the last lecture here for chapter 10 is going to be over section 7, and we're going to be discussing the vector nature of angular quantities. While we've discussed angular velocity up to this point, we've never really given it a direction. I mean, we've always kind of thought about it as the change in the displacement over time, but which way is it actually pointing? The vector angular velocity is a vector quantity whose direction is that of the axis of rotation and whose magnitude is the scalar angular velocity. The sense of the vector omega is given by the right-hand rule. When a body rotates around an axis of symmetry, the vector angular momentum is given by the vector of angular momentum is equal to the moment of inertia times the vector of the angular momentum. As it turns out, both are pointing in the same direction. So in terms of the vector torque and angular momentum, the basic dynamic relationship for the rotation can be expressed as this. Basically, it's what we've learned up to this point. We're just slapping a vector notation on it. Now, let's go to the section here and let's kind of talk about how to spot which way these things go. We're going to, again, use the right-hand rule. You're going to get sick of hearing the right-hand rule. If you curl the fingers of your right hand in the direction the object rotates, like let's say we have a gear here, and we rotate the right hand in the direction, rotate those fingers in the direction of the gear as it's rotating, the thumb is going to give you the direction not only of the angular velocity, but also of the angular momentum. You have to use the right hand. It's the only one that's going to give you the correct orientation of how this works. So don't try using your left hand to do this. That's bad juju. You don't want that. What you want is to use your right hand, and you're going to curl your fingers in the direction of the angular velocity, or pardon me, you're going to curl your fingers in the direction of the rotation, and that will give you the direction of the vector of the angular velocity. For torque, you're going to curl the fingers of your right hand the direction the torque would cause the body to rotate. So if you've got something here, just like a screw, and it's rotating this way, put your fingers like that. The thumb is going to point in the direction of the torque. Right-handed screws are threaded so that they move in the direction of the torque that's applied to them. So if you try to balance a stationary top on its point, it's going to fall over. But when it's spinning, it's going to balance. And why is that? And why are bicycles tippy when moving slowly, but stable when moving fast? The general answer for that is it's complicated, but we're going to go a little way towards understanding it. So for a symmetric body turning around its axis of symmetry, the magnitude of the angular momentum is going to be the moment of inertia times the angular velocity. The corresponding relationship between vector angular momentum and vector angular velocity is given by this. Basically, we're going to take vector notation, we're going to slap it on the angular momentum as well as the angular velocity. The moment of inertia is something that deals with mass, so that does not have a vector rotation. So we can define a vector torque that is related to the rate of change of vector angular momentum with respect to time by a vector equation analogous to equation 10.10. So basically, we're going to take what we've seen there and we're going to slap vectors on it, and we're going to take this delta t and multiply it by both sides to change this around. So in the problems we've worked out so far, both torque and angular momentum have always had the same direction. So only one component of each vector quantity is different from zero. But equation 1017 is going to be valid even if they have different directions. Then the directions of the axis of rotation may change, as with a spinning top, and we have to choose the vector nature of the various angular quantities carefully. So an example of a three-dimensional application is going to be the gyroscope. This figure right here is going to represent our gyroscope. So we're going to set the flywheel spinning by wrapping a string around a shaft and then pulling. When the shaft is supported at only one end, which that's what you see here, the axis undergoes uniform circular motion in a horizontal plane. In other words, it's going to spin like this. While the flywheel continues to spin around the axis. This combined motion of the axis and the flywheel is known as the precession. It can be quite unexpected when you see it for the first time. Intuition suggests that the free end of the axis should simply drop if it isn't supported. And indeed, if the flywheel isn't spinning, that's what you're going to see. But the vector nature of angular momentum is key to understanding the horizontal motion of the axis when the wheel is spinning. So, when the flywheel and its axis are stationary, they're going to fall to the table's surface. That shouldn't surprise anybody. When the flywheel spins, it and its axis float in the air while moving in a circle around the pivot. So you've got circular motion of the flywheel around the axis. That's its precession. You've got the flywheel, you've got the axis, and you've got the rotation of it. And this is going to be the path followed by the free end of the axis. This is a good discussion on rifling, putting a torque on a shell. When you do that, you're going to be able to cause the shot to not only fly further, but also be more steady. And basically that means spinning the shell as it travels. So let's take a flywheel that is not rotating. The weight of the flywheel is going to cause a torque around the pivot, causing it to fall along a circular path until its axis rests on the table's surface. So you've got the weight here, you've got the moment arm here, you've got a normal force up here. If you take the cross product of those two, it produces a torque which goes this way, and the path of the free end is going to fall. In falling, the flywheel rotates about the pivot and thus has an angular momentum, and in other words, the angular momentum is going to be this way. Now, if we take the flywheel and we start to rotate it, the system starts with angular momentum parallel to the flywheel, axis of rotation. You still have the torque here due to the weight, but you also have the initial angular momentum due to the rotation of the flywheel. In other words, that rotation, that angular momentum is going to be out this way. Now, the effect of the torque is to cause the angular momentum to precess around the pivot. The gyroscope circles around the pivot without falling. So you can see the change in the angular momentum as it moves around. The magnitude isn't changing, but the direction is. So the gyroscope has a definite non-zero angular momentum described by this vector. The change in angular momentum in a short interval is given by this particular equation 10.17. This is the direction of the angular momentum is going to be the same as that of the torque. After a time delta t, the angular momentum is this, basically what you started with, plus the change. And as the vector diagram shows, this means that the gyroscope axis has turned through a small angle, and it's given by this. We see that the precession is required by the torque angular momentum relationship. The rate at which this happens, if you take this divided by delta t, you end up getting big omega, and that's going to be measured in radians per second. This is a precession, and this is going to be how fast it rotates.